Hello, welcome to Calculus 2, which is a course that I'm offering online based on the free textbook by Openstax. Okay, this one, which you can download from their website or from Amazon and stuff like that. So then once you have the textbook, my course is designed such that you don't need any other help, okay? I should teach enough stuff in here so that you can learn calculus with nothing more than the book and the videos that I'm making. Plus, it's very important that you do all the homework I assigned. That will make you completely proficient in learning calculus. This is just this is a class that's taught as for math as a hobby. So in this particular course, I'm teaching calculus as a hobby. And you might think, how can calculus be used as a hobby? It can, okay? It's just, that's how it used to be. Calculus used to be a hobby for people like Isaac Newton and other such people. That's, as far as I know, they didn't know what calculus is good for or used for. They're just doing it because it's fun. And I want to continue that tradition and continue to teach calculus as a fun pastime. So that is the focus of this course. As a result, I won't be teaching you how to pass some tests. I also won't be designing any tests. The whole thing is done so that somebody who is, for example, retired at home and instead of doing something like knitting, they can learn calculus. Okay, the course does require some prerequisites that you need to know algebra, of course, trigonometry, pre-calculus, and of course, calculus 1. And if you haven't taken those classes, please start over there first. And I'm planning on preparing videos for those classes as well. But if you have finished all those things, and let's get started on doing calculus 2. How exciting, right? I mean, it's tremendously fun. And people don't often know this. First, let's look at chapter 1. This is on page 6 or something. Yeah. And for chapter 1, it's just a review. So I'm going to highlight these points that are taught in previous sections, in calculus 1. If the review seems incomprehensible to you, that will mean one thing. It was a long time ago that you took calculus 1 and you've forgotten most of it. In that case, please go back to redo calculus 1. And there's nothing wrong with that. If only parts of chapter 1 seems puzzling to you, then just go back and review that specific part. Otherwise, we should just quickly highlight chapter 1 and then move on to actual calculus 2, right? And instead of being stuck in the past. So first, I wanted to talk about on page 6 is the sigma notation. The sigma notation just means, let's say you have 20 objects added together, okay? That you have, say, you want to add 1, 2, 3, all the way up to 20. Instead of writing it all out as your book did on the top line, you can simply use the summation notation. That's the sigma symbol from Greek, where you say, well, I'm adding from 1 to 20 the number I. That is, I will progress one at a time from 1 to 20, and then I want to add all that stuff up. And so that's the sigma notation. And and it doesn't have to be just 1 to 20. It can be any number. Okay, each number, look down here, where it says you add a bunch of A's together. A can be any number. And it's just the name has a title. That is, A1 is the first number, A2 is the second number, and so on, until you add up to AN, the nth number. And then at the end of that, then you have a bunch of numbers added up. And that's called the sigma notation, which is a shorthand for adding a whole bunch of stuff. Now, next, let's look at some properties of the sigma notation. The sigma notation just means add stuff up, and as a result, the addition properties all apply. For example, if you, what's the first one say? If you have a constant multiplied, if you add up an n number of constants, the first rule, that's just n times the constant. The second rule, if you had a constant multiplied to each and every member, okay, it has to be all the members of your summation, you can pull the constant out and just use the constant to add up the sum of all of them. and that often make the work a little easier. If you have a summation of 2 items, due to the properties of addition, you can add up each item individually and then put them all together. And the same as, what's the last one? Subtraction, same principle. So next, let's review some more. What is that last one? And the last principle is, that's also obvious, is if you add a bunch of stuff from 1 to n, you can add up part of it, okay, from 1 to m is some number less than n, and then keep adding from n plus 1 all the way back up to n. So it's okay to break up the summation into 2 chunks. And sometimes there's a need for doing that. So that's that. Now the next thing is that the rules of, there are certain formulas. Okay, these formulas are proven with mathematical induction in probably pre-calculus. So we're not going to repeat them here. Although this is also all this stuff is done in calculus 1. All right. So if you want to see the details, you can look at here, or if it doesn't mention it, look at calculus 1. Although and now calculus 1 didn't even prove these stuff. It's proven in pre-calculus. But anyway, what we're going to do with this stuff is we're just going to use it. We're not going to prove them anymore. So reinvent the wheel and prove them. So you just have to look at these formulas. You don't even have to memorize them, except maybe the first one. The first one is so simple and easy that it might be beneficial to memorize it. But if you don't, it's no big deal. So the first formula is if you add from 1 to some number, a billion or something, and you don't have to do the direct addition. You just follow this formula, plug a billion into n, therefore n times n plus 1 over 2. Then you come up with the answer. Don't have to add that many times. Similarly, if it's a bunch of sum that's I squared, then here's a new formula for it. And then the same as I cubed. If you have a bunch of cubed added up, here's yet another formula for that. So those formulas are quite useful. Well, if you ever need to add that stuff up, that is. So next, let's look at the concept of the Riemann sum. The Riemann sum is about calculating the area under the curve. So here you have some curvy curve, right? And so what is the area under it? Well, there's no formula that you have learned in the past, such as area of the circle is pi r squared, for example, area of triangle is base times height over 2. But there is no direct formula to calculate this. How would you calculate it? The way you calculate it then is you slice that same graph, okay, into a bunch of rectangles individually, and then you will calculate the width, each individual long, slender rectangle, base times height, and then you add them all up. Okay, the base times height end up being the base is called delta x. And delta x depends on how much you slice the stuff. The more you slice that area, then smaller the delta x becomes. And then n times the height is just f of x at that point, or at some endpoint next. Some endpoint, doesn't matter which one. You can pick the left one or the right one. Yeah. So then you approximate the area, and area gets better and better the more you slice it. So your approximation gets to be more precise. And of course, you are logging a lot of work, right? If you slice it into 1,000 slices, that's going to wear you out, even if you use the computer to do that. But in any case, the sum has a name. It's called the Riemann sum, and that is how we calculate the area under the curve. And then that area, of course, is approximated. But as you let n go to infinity, then your calculation become more and more accurate. And the definition of when you do calculate it into infinite, slice it into infinite number of slices. Look at this. Okay, let's see. My camera will focus. Yeah, there it is. So the more slices you get, as you can see, the more precise your approximation for under the curve has become. And as n goes to infinity, when is n going to infinity? Here we are. So finally, if you let n go to infinity, that is the area under the curve. A couple of pages later where you find this formula. And that's the definition of the area under the curve, is you let n goes to infinity and calculate that sum. Now that doesn't sound very easy to do, and it's not. However, there is a trick that we can do to come up with that. So let's go to make that process sometimes easier. And that is called the definite integral. Let's go to section 1.2, which is on page 27, where we have the definite integral is defined as exactly the sum of the Riemann sum from sum a to the boundaries, okay, of your area under the curve as n goes to infinity. As you slice more and more slices, then the area under the curve converge into the area to be exact, okay? The Riemann sum is just an approximation, but as n gets huge, then your approximation becomes becomes extremely accurate as the way limit goes. Okay, you can make it as accurate as you want within within the error tolerance. So that is the definition of the definite integral. That the definite integral means the sum of the Riemann sum of the area under the curve. All right, and next, there is a basic formula, that is, if f is on the next page, if f is continuous, then you can calculate the area. Okay, if f is continuous on a closed interval from a to b, and that is just something that we believe, but it's also something that you need to bear in mind. That is, if f is not continuous, especially if f took off to infinity or something, then you're not going to be able to integrate. At least the integral doesn't work. You might come up with all kinds of weird or wrong answers. But as long as it's continuous on the closed interval, that means it doesn't go off to infinity at the end point. Okay, so then it's totally integrable, which means you can calculate the area under the curve. Okay, next we will see the area under the curve. Of course, has a specific quality. Is sometimes you might end up with a negative area, like this one. The one area on top is positive. On top of the x-axis, the area below the x-axis is negative, and that's okay. There's nothing wrong with having a negative area. And so and as a result, sometimes if you want to find the total area, whether it's positive or negative, you have to take turns to calculate the positive area, and then to take care to calculate the negative area, and then add them up, and never mind the sign. Instead of integrating all the way through, because then the positive will cancel out the negative, and you end up with whatever the result is, which might not be what you want. What you want is the total area. If you don't care about that, then it's okay, right? That's just you only want to know what the net area is, the positive minus the negative. So next we are going to, what's this? Yeah, that's nothing. So let's flip over to page, what is that? 35. So on page 35, we have certain rules concerning the definite integral. The first rule is, of course, that if you integrate from a to a itself, that is your Riemann sum has no width. Okay, then there's no area if there's no width. Then your integral will be 0. Now, the second rule on the next page is that if you flip the endpoints, they're called the limit, top limit, bottom limit. Let's see, the top one. Okay, if you flip the endpoints around, that is, can you see that? Let me make it a little bigger. Okay, if you exchange the top limit, that is a and b, the limits of integration, they're called. If you flip them around, all that you do is just stick the negative sign in front. Okay, that's the only difference. The next rules are are pretty obvious because the Riemann sum is based on addition. So therefore, if you integrate, say, two functions together, that's the same as integrating each one individually and then add them up, the same as subtraction. And then another one is if there's a constant multiplier, that in the integration, you can take the constant out. See, like, this one. Yeah, the constant can be taken out in the integration, but that's all. Okay, nothing else can be taken out. If there's an x in there, you cannot take it out. Only the constant. And then the last formula is that if you integrate from a to b, you can integrate to some midpoint or some point in between, from a to c, and then going back, continuing integrating from C to B. That's because an integration is calculating area under the curve. So you can calculate part of the area and then continue finishing and doing the rest of the area. However, the way it works out, C doesn't have to be between A and B. C can be anything. As long as within the domain definition, this formula works. It just works out because of the negative area situation and stuff. Okay, but that's something that you should be reviewed if you need to. And then the next thing we need to do is the comparison theorem. Okay, I will quickly mention it. The comparison theorem is quite obvious. That is, let's say if you have the first one, which says that if you have a function that's bigger than 0 for the entire interval that we care about, then the area under the curve will also be bigger than 0 or equal to 0 if the function is bigger or equal to 0. Okay, that seems pretty obvious. And then part B, it says if you have one function that's bigger than or equal to another function the entire time from A to B, then the area under the curve is also bigger. Okay, one's bigger than the other. And then another, that seems obvious. And then one more one is that if the function is between two values for the entire time from A to B, then the area under the curve is going to be of the function is going to be bigger than the small value times b minus a, that is the rectangle under it, and then the integral be less than the big value times width or that is the area over it that contains f of x. So that's the comparison theorem, which is again fairly obvious. Next, we are going to talk about the average value. The average value of from A to B is defined as the integral of f of x divided by the length of the area. Okay, so that comes up with some sort of average value. All right, so that's that. Let's keep flipping. Okay, we're done with 1.2. Flip. 1.3. Mean value theorem. All right, the mean value theorem states for integrals, that is, if you have an average value from A to B, then there exists at least one point C between A and B, could include endpoints, I think, such that the function of the value of the function as C equals to the average value. And all right, so that's that. Why that is true is also fairly obvious. And so having said all those things, let's come to the important point of this chapter, the fundamental theorem of calculus, which is very exciting. The fundamental theorem of calculus states that if you have f, which is continuous over a closed interval from A to B, well, our discussions are that way, right? And then the function f is defined by the integral from some point A to x of ft dt. That is, if the function is defined from A to wherever x is that you are integrating. And what that means is, you notice there are two variables in this definition, but the t is just called a dummy. What happens is that for each x that you need to figure out what the value is, you have to do the integration from a to x, and that will give you the value of the function big F. So then that sounds like a complicated definition, and it is, but it can be done when You just integrate for each point. Okay, anytime you need to know what the value of f is, you do your integration, figure out what the area is under the curve, and that's your function f. So the t is just the variable of integration, and it's not directly related to the function f. That is, you can use t, u, anything, right? Just as long as you do the integration under the curve. Now, the fundamental theorem of calculus says that if you define big F this way, then big F has a very unusual and cool characteristic, because then the derivative of big F is exactly little f for the entire interval. So that means the derivative, which is the slope of the big F at the point x, just happens to be the value of little f at that exact same point x. So that's the fundamental theorem, which means the antiderivative is directly related to the area under the curve, is what this statement means. All right. So with that, we can figure out a lot of areas much easier if you can find the antiderivative. So flip. Let's go to the next point. The next point says that the evaluation theorem. The evaluation theorem then states that to evaluate the actual area of from A to B of small f, all you need to do, if you can, is find the big F, that is small f's antiderivative, and evaluate its value from B and subtract it from its value at A, and that would be the area under the curve. So the area under the curve is done by calculating the antiderivative and then calculating the difference of the antiderivative at those two endpoints. And that's part 2 of the fundamental theorem of calculus. All right, now so next we have, what's this? So we're done with 1.3. Please flip the page. Go to the next thing, integration formulas. All right, 1.4. I'm now at page, 64. The various integration formulas are, well, first we'll talk about net change theorem. Because of the evaluation theorem, there is something called the net change theorem, which I don't even think is necessary to mention, okay? Which is just rewriting the evaluation theorem slightly, which says that being that the integral of big F prime x dx equal to fb, big FB minus big FA, then big FB, you can rewrite it by slapping the minus FA on the other side of the equation. It will be equal to big FA plus the integral. Okay, that seems obvious. So, but your book thinks that's worth mentioning, and you can give it a name called net change theorem. So yeah, I guess we'll do that too. Now next we have the integrals of even and odd functions. Being that the integrals are areas under the curve, and also the integrals of areas beneath the x-axis are negative, then you naturally have this property of integrals that can sometimes come in handy. That is, if your function is even, that is, their two sides are identical across the x-axis, and if you happen to be integrating from a negative value to the positive value of the same thing, that is like from minus a to a, then that's the same as doubling integrating just from 0 to a, because the two sides are identical. Now similarly, if your function is odd, which means that the left side is the negative to the right side, but otherwise the same, then the integration from minus a to, if you happen to be integrating from exactly from minus a to a, then the integral will be 0, okay, because the two areas are exactly the same, except that one is below the x-axis and therefore negative. Then they will cancel each other out exactly, and so your integration becomes 0. Now flip. Let's go to the next part. Come on, flip faster. Number 15, the substitution trick. Okay, the substitution trick is done a lot in Calculus 1, and it's an important trick for you to know. So if you're not familiar or have forgotten the substitution trick, most of it, then please just do a few examples in this section, and you will catch up. the substitution trick, it comes from the chain rule. That means if you have your integrand, I think that's what's called the function inside. If your integrand happens to look like the chain rule, that is your antiderivative, you can see something that which if you take the derivative and then apply the chain rule, it looks exactly like the integrand. Okay, in that case, then you can reverse the process, and then the integration is just, think about the chain rule backwards, right? It's just the big F times the small function is, of course, always plus a constant. Now you can see how this makes sense simply by taking the derivative of the big F and then applying the chain rule in the derivative, and you'll see that it directly becomes the integrand. So when you use the U substitution, what you do is you choose some kind of a U and then make it come out like here. Okay, you choose some kind of a U equals to g of x right there in the middle. You choose some kind of U equal to g of x such that du equals to g prime of x dx. That way your entire integral is taken care of. Okay, you plug it in there, and then so then the f of g of x becomes f of u, and then the g prime of x dx becomes du, and then the whole thing will come out and your integration becomes much easier. The substitution rule is good for some problems. It's just another trick in the bag, but remember, integration is not guaranteed. There might be a problem that you can't integrate no matter how many tricks that you pull out of your bag, but the tricks are still good for a lot of functions. So that's why we learn them and memorize how to do it. Now, if you can't quite remember how this is done, please do the examples in here until you feel familiar with it. Like example 1.30, 31, 32, 33, 1.33, and so on. What is that? Okay, the next one is that when you do use substitution for a definite integral, what we have done so far is just the indefinite one. If you do it for the definite integral like this, don't forget to translate the endpoints from a to b to u, okay? Because now you're doing u, so you have to figure out when x is a, what is u? Then u becomes g of a. Okay, you got to remember to do the transfer. And if x is b, u becomes g of b. So and then you integrate accordingly. If you forget to do that, then you'll come up with a completely wrong answer and can't figure out why. So let's move on. And then we'll do the examples. If you feel rusty about all that stuff, it will a couple of examples will bring you right back. And then, so next, let's move on to section 1.6, where we're doing, this is on page 93. Okay, how do you integrate exponential functions? That is e of x. Specifically, the derivative of e of x is just e of x itself. Therefore, the integral of e of x is also the e of x itself, being the integral is the reverse action of the derivative by the fundamental theorem of calculus. Similarly, if you have a base that is an e, that's just some number a, then the formula is very similar, except that you have to adjust by dividing by the natural log of a, then you're good. Okay, so that's the integral. Next, flip. Come on, where's the next thing? Oh, there's nothing. Well, where's the natural log? Did I miss the natural log? I must have missed it somehow. Yep, I missed it. Let's go to page 99. Okay, 99 tells you how to integrate how to integrate the natural log. The formulas for natural log is the integral of 1 over x is natural log of x. The integral of natural log is the other thing. If the integral of log to some other base, then the natural log is that thing. Anyway, is, well, basically the same as the natural log formula, except you have to, again, adjust it by dividing by natural log of c. And as all indefinite integrals, you have to remember to add the constant because, because derivatives are the same up to a constant. So then of any function that's up to a different by a constant. So that's All right. The integral of natural log is less intuitive, I guess. So then, if you feel rusty about this section, do some or all of the examples, and that should be plenty good for you to be ready for the rest of the course. Next, the inverse trigonometric functions. The inverse trigonometric functions has some useful integrals that looks something like this. They're not used as much. Well, at least in the course, they're not. But they're still good to know. If you see an integral that looks like that, then you know to look up the inverse trigonometric functions, and then that's what the antiderivatives are. It's probably not necessary to memorize them. You just because they're very similar and it's easy to get confused which one is which. You just look it up when you need them. Okay, next. That's 1.7. Okay, that's about it. That's the end of my review for chapter 1, which is just a recap of chapter 1 of Calculus 1. I should have mentioned in the beginning of this course beginning of this class that if you know Calculus 1 very well because you just recently finished it, then it's not necessary to look at this video. But but I forgot to mention that, so here we are. So next, we will go to chapter 2, and where I will go into detail. The reason this hour seems to be rushed through because it's just a review, right? I don't have to explain any details.